All right, so we're going to talk about counting. And this is a really cool topic because it takes you all the way back to the very beginning of your mathematical journey. Counting is one of the first things you learn to do before you really even learn how to do math. You can just memorize 1, 2, 3, 4, 5, all the way up to 10, to 20, then up to 100, and keep going. But what we really mean here is where we have a situation where there are some number of outcomes or choices, and we want to figure out how many there are. So the situation could be choosing different options for a car that you're buying. Maybe there's a color, maybe there's, you can pick manual or automatic. All of these choices, you want to figure out how many possible choices there are for this type of car you want to buy. Or maybe you're at a restaurant and you're trying to figure out how many options there are to order a particular type of dish. So that's really what we mean here by counting. We're not literally going to be just saying our numbers in order. We're going to try to figure out which number represent the number of choices or the number of outcomes in a particular experiment. So let's look at the different types of counting that we'll be doing. Okay, so there are lots of different types of counting. There are lots of different counting strategies. In fact, this is an entire branch of mathematics called combinatorics, and that's just a fancy word for counting. So we're not going to dive too deep into it, but we're going to look at three types of situations where you want to do some counting. And we'll look at, I hesitate to say formulas for these sorts of situations. I think about it more thinking about the way you should think about these situations. Okay, so first, we'll think about when you have independent choices or independent experiments, how you count the number of outcomes or the number of choices. Secondly, we'll talk about combinations. Combinations, you can think about, are choices where I take some set of objects from a larger set of objects. So if I reach into a bag and pick out whatever's in the bag, I'm taking a combination. And the thing with combinations is that the order that I select things doesn't really matter. And then finally, third, we'll talk about permutations. And permutations are just like combinations where I'm taking out objects from a set of objects, but the order in which I take them out is actually going to matter. So these are the three situations we're going to talk about, and let's get started. Okay, so the idea behind independent choices is really simple. If I make two independent choices, or more than two, but let's just think about two for now, and those choices are independent, and we'll look at what independent means mostly by looking at an example, okay, but if the two choices are independent, then all I do is multiply the number of choices of each of the individual cases, and that's the total number of choices. So I think an example is going to take us really far in understanding what this means. So suppose that I'm at a restaurant and there are three choices for an entree. So there's a hamburger, hot dog, burrito. So that's three entree choices. Okay. And then there are four side choices: fries, onion rings, salad, rice and beans. 1, 2, 3, 4. And the key thing here is that the choices are independent. Okay, so what do I mean by that? Well, it means that if I pick a hamburger, I can still pick any of the sides. The choice of the entree doesn't limit the choices in any way for the sides. Okay, so how many total choices are there for meals? Well, this law of independent choices says that all I do is multiply 3 and 4. And what does that give me? That gives me 12 meal choices. Now this is a really simple fact. I think a lot of people could come to this answer on their own if I gave them this example. But it's also very powerful. If you can separate two experiments as independent, or two choices as independent, then it's nice to know that all I need to do to figure out the total number of choices is multiply, even if the individual experiments are very complicated. Okay, so let's talk about combinations. So a combination goes like this. I have a set of n objects, and those objects could be anything, but they're distinguishable, I guess. So we say a k combination is an unordered selection of k of those objects. Okay, so let's just go ahead and jump down to our example just so we have some better language to sort of talk about what a combination is. So the example says, how many ways can I form a committee of 5 students from a class of 12? So in this case, our set of n objects is 12 students. So it's all the students in the class, and I'm making a selection of 5 students. And now because it's a committee, it doesn't really matter which student I pick first or last. I'm just selecting 5 to be in the committee. So the order doesn't matter. So this is a 5 combination. So choosing 5 students is a 5 combination from this class of 12 students. Okay, so notationally, if you have a combination, the number of combinations, so of a set of n objects, the number of k combinations is denoted like this, so the c with the nk. It's equal to something that we've seen before, and that's this particular binomial coefficient. So this is read n choose k, so n choose k. And that's really nice to say n choose k when you see this, because that's telling you exactly what you're doing. I have n things and I'm choosing k of them. Okay? Very simple. That's what a combination is. And so what does this mean? Well, it means I take n factorial. Okay, so remember the factorial is just the product of the numbers up to n. So n times n minus 1 times on down. So, for example, 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. And then we divide by k factorial, and then we also divide by n minus k factorial. Now, I'm not going to get into exactly where this formula comes from. It makes a lot of sense. I mean, you can break it down really easily. But just for the sake of time, we'll just sort of take this as our formula. I mean, what you're really doing is you're kind of taking a k permutation and then dividing out the order. That's one way to think about it. But for now, this is the formula. Okay, so how many ways can I form a committee of 5 students from a class of 12? Well, it's 12 choose 5, which is 12 choose 5. That doesn't really mean anything. I'm just using the different notation that you'll see. Sometimes you'll write it as the binomial coefficient, sometimes it's written like this. But it's equal to 12 factorial over 5 factorial, and then also divided by 12 minus 5 factorial. So 12 minus 5 is 7, so we have 7 factorial. All right, and so what I like to do, instead of, I mean, if you type 12 factorial in your calculator, you're going to get a really big number. So this is what I like to do. I like to do some simplification. So this is 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. all over 5 factorial is 5 times 4 times 3 times 2 times 1. And then look what happens when we divide by 7 factorial. That's 7 times 6 times 5 times 4 times 3 times 2 times 1. But we have a lot of the same factors on the top and the bottom. So you have a 7, 6, 5, 4, 3, 2, 1. So all we're left with is 12 times 11 times 10 times 9 times 8 divided by 5 times 4 times 3 times 2 times 1, which we already know is 120 actually. So let's just do 12 times 11 times 10 times 9 times 8. And we get a more manageable number. So 95,040. And then 5 times 4 times 3 times 2 times 1 is 120. And it's sort of an amazing fact. I mean, it looks like this number is a fraction, but actually this number is always going to be a whole number. And in this case, that whole number is 792. So there's 792 ways I can take a class of 12 students and just select 5. And this is really cool because what you're seeing is in small cases, you can actually write down all the combinations. And this is sort of what we did, if you watch the video on looking at sample spaces, you can just write down in small cases all of the possible outcomes when I roll 2 dice. It would take me a really long time to write down all 792 combinations, if I listed out all 12 students and then I just started selecting 5 students. I would have to be really careful not to count the same combination twice. It would be a mess, but this is just saying, well, I know that there are 792 possible combinations. Okay, so permutations, very similar to combinations. The only difference is that my selection of my k objects from my set of n objects is now ordered. The notation is very similar. So it's just this p, so n, and then it's not choose k, it's n permute k. And it's equal to n factorial over n minus k factorial. That's the total number of k permutations from an n set. And notice that this is equal to, sometimes this is useful, n choose k times k factorial. So if you want to relate it to the combinations, you could just take the k combinations and multiply by k factorial. So in our example, how do I know whether I want my selection to be ordered or unordered? Well, look at this example. How many ways can I select a president, vice president, and secretary from a class of 12 students? Now, this is a selection of 3 students from the class of 12 students. But notice that who I pick first is going to be the president, who I pick second is going to be the vice president, and who I pick third is going to be the secretary. Now, that differs from a committee because who I pick first, second, and third, there's no difference, right? The order doesn't matter. But here the order does. So this is a 3 permutation from a set of 12 students. So how many are there? There's 12. Permute 3. That's going to be 12 factorial divided by 12 minus 3 factorial, or 9 factorial. And again, I can sort of simplify the computation if I realize that the top is 12 times 11 times 10, and then times 9 factorial. all over 9 factorial, because remember that 9 factorial is just 9 times 8 times 7 all the way down to 1. So I can write 12 factorial like this and actually cancel the 9 factorials. And you see now the answer is probably what you would expect. It's just 12 times 11 times 10. And this is really easy to think about because if I have my class of 12 students, I first have 12 independent choices for president. But once I pick a president, I only have 11 independent choices for vice president. And then once I pick vice president, I only have 10 independent choices for secretary. So it is 12 times 11 times 10. And what is 12 times 11 times 10? Let's figure it out. 1,320. So there are 1,320 ways to select president, vice president, and secretary from a class of 12 students. And that's all we're going to talk about with counting. So hopefully this gave you a nice overview. There's a lot more that you can dive into in this world of combinatorics, but that should get us started and give us enough to really answer a lot of interesting probability questions that involve counting outcomes, whether that's favorable or total.